Good evening and welcome to our third lecture in EE274 OE197E. So for today, we'll be discussing discrete time system representation. So first, we'll be defining what are discrete time systems and what are the ways to represent these systems, either mathematically or graphically. And then we'll try to classify these systems according to their properties, and then we'll show you some examples of discrete time systems. Now, discrete time systems are systems involving discrete time signals and their related processes and operations. You have this block representing our system. So signals going into our system are called inputs or excitation, and it's denoted usually by x of n. The signals that are going out of the system are called the output or the system response. One way to describe our discrete time system is through difference equations. And by solving this difference equation, we may be able to get any type of response for any given input. So shown here are some examples of difference equations. These are the ways to represent discrete time systems mathematically. So we have our outputs and input terms. Now another way to describe discrete time systems is through block diagrams. So in this method, we will describe the system using a graphical approach, using our block operators and their interconnections. So in the previous lecture, we have already discussed some of these blocks. Right now, we'll be adding new more blocks such as the cascade connection, wherein two blocks or two systems are cascaded. So when we have this cascade, we denote the operation as a discrete convolution operation. Now if we have a parallel connection, it's also the same as adding the two signals or the two responses. An example is shown here. Our y of n is equal to 0.25 y of n minus 1 plus 0.5 x of n plus 0.5 x of n minus 1. So the first term is a feedback term denoted by this connection. Y is being fed to a delay block z to the minus 1 and multiplied to a gain of 0.25, which is added to the x terms. So the x terms are x of n multiplied by 0.5 and then another term delayed by 1 unit and then again scaled by 0.5. So in figure B, it's also the same system, and we can see that a 0.5 multiplier was placed after the summing block, which is still mathematically the same. Here we can see that representing discrete time systems are not unique, and especially when we have linear time invariant systems, we can represent and exploit multiple mathematical properties to denote different configurations for the same system. Let's go on with the system's classification. Here are some of the common classifications for discrete time systems. First is system memory. We say that a discrete time system is memoryless if the current output depends only on the current input and sample index, while systems with memory, also called dynamic systems, depends on the past outputs and inputs and possibly future outputs. Let's try to classify these given systems. The first one, y of n equals x of n minus 1 plus 2 of x of n minus 2, depends on previous values of our inputs. For example, we want to find y of 0, we need x of minus 1 and 2x of minus 2. That means this is a dynamic system. B is also a dynamic system as it depends on the previous values of our outputs. C only needs the current input x of n, while D is just the flipped version of C. So we say that C and D are both static systems. Now, under dynamic systems, we say that a system is recursive if the output is dependent on the input and past output values. Back to our difference equations, we can see that A is only dependent on the past input, so it is non-recursive, while B depends on the previous output, which means B is a recursive system. Let's go on with time invariance. Time invariant systems are systems in which applying a time delay on the input directly equates to a time delay at the output. If this is not the case, then we say the system is time varying or time variant. Let's take a look at time scaling and folding. If we time scale and fold, we can see that applying a shift with a time scale doesn't follow time invariance because the delay also gets time scale. And we say that this system is a time varying or time variant system. Next is our modulator operation. Here we can see that our input x of n is modulated by another cosine function. And if we try to time shift our x of n, the time shift does not apply to the modulating function. And therefore, this modulator block is a time variant system. Here in our third example, we see that applying a shift in this particular difference equation directly translates to a shift in our original output. So we say that this particular system or this moving average system is a time invariant system. Third is linearity. So a system is linear if and only if it follows this superposition criteria. A graphical representation of this is shown here. If we try to multiply our two signals x1 and x2 before adding and processing, it should be the same as x1 and x2 being processed first and individually multiplied to their gains before adding them together. So if this y of n is equal to y prime of n, we say that the system is linear. So let's try to classify these difference equations. So for these examples, you can prove this at home. Our first example is linear, but this is also a time varying system. Our second signal is a linear function because our square here is just applied to the argument n, but if we apply the square to our input, it's already a nonlinear system. Example 4 shows the typical linear equation, and for our last example, e to the x of n, we see that it is an exponential function, thus it is nonlinear. Moving on with causality. We say that a discrete time system is causal if the output depends only on the current and past inputs. And if it does not meet this criteria, then we say the discrete time system is non-causal. So here we have two difference equations. The first equation on top, we see that when we try to get a particular output, y of n, for example, y of 0, we need x of 0, x of minus 2, and x of minus 20, which means it only needs the current input and the previous inputs. So it means this is a causal system. However, for our next difference equation below, to get y of 0, we need x of 10, which is a future input, our current input x of 0, and a previous input x of minus 3. Therefore, this system is a non-causal system. Shown here are 7 different equations, so you can try to prove this at home. For example A, let's try to look at y of 2. In order to get y of 2, you need x of 2 squared, which is x of 4, which means you need to get a future input. This system is non-causal. In example B, we already know that this particular system is causal since it only needs the current and the previous input. Example C runs from negative infinity to n for our accumulator, which means all the previous inputs are considered. This is a causal system. Example D is a folding function. If you try to get y of 1, you need x of minus 1, which is the previous input. So all of these requirements follow causality. For example E, this is just an amplitude scaled input, so this is a causal function or system. Example F needs x of n plus 4, which is a future input, so this is non-causal. And last, our example G is a non-causal system because if you need y of 2, you need x of 4, which is a future input. We also classify systems whether it is stable or unstable. So we say that an arbitrarily relaxed system is bibostable or bounded input, bounded output stable if and only if every bounded input produces a bounded output. So if we don't meet this criteria, we say that the system is bibo-unstable. We can show that this particular difference equation is bibo-unstable. We need to try a bounded input such as u of n, a step function. We place a unit step as our x of n and we try to simulate our output y of n from n equals 0 onwards. Here we see our system is continuously increasing, and even just with 3 values, it's almost parabolically increasing. So we say that this particular system is bibo-unstable. So under stable systems, we say that the system is passive if the energy of our output is less than or equal to the energy of our input. And for finite systems, for finite energy signals, at most we can have the same energy in the output signal. Last is our classification of lossy systems. So we say that a discrete time system is lossless if the energy of our input is also the same as the energy of the output. And if it's less than, then it is a lossy system. An example of a lossy system is a downscaler or a downsampler. So hopefully if you've done the lab experiment, you can verify that the length of the signal decreases as you downsample. And since you decrease the length of your signal, you tend to have less energy compared to your previous signal. So we say that these systems are lossy systems. So next I'll be showing you some examples of discrete time systems that we'll be working on in this course. Shown here is a difference equation describing this particular system, and shown below is the block diagram representing this moving average system. So for moving average filters, you only need the inputs, their delays, and the weights. Moving average filters are usually being used to smoothen out noisy discrete time signals, as shown here in the figure. When you have our S of n, our original signal, added to D of n, our noise, we get our X of n, which is the noisy signal. And if we try to use a moving average, we can actually have a smoothened version of that X of n. Next is an autoregressive filter or an autoregressive system. For autoregressive systems, you usually have your feedback terms, your y of n, the delay blocks, and their gains. There is one particular class of systems called the autoregressive moving average systems. These ARMA systems are comprised of an autoregressive block and a moving average block. Our last example here is an upsampler or the interpolator system. So here we can see that x of n is being upscaled to xu of n, and then we try to interpolate xu of n to get our y of n. So this is similar to the lab experiment you've seen. When you try to upsample, the upsampler gives you more data. However, you can see that those data are just added zeros. In order to reproduce the desired signal, you need to interpolate the values of our sequence. And this is particularly useful in upscaling images. So here, a 512 by 512 size image was downsampled into 256 by 256. By using bilinear interpolation, we can still upsample to the original size with minimal loss in quality. In summary, we've seen that discrete time systems can be represented either mathematically using difference equations or graphically by using block diagrams. We also have different classifications for discrete time systems depending on the properties such as linearity, time invariance, recursion, causality, stability, and energy losses. And we've shown some examples of discrete time systems such as the moving average filters, autoregressive systems, ARMA systems, and interpolator filters. For further reading, I'd recommend these chapters of our references. And that's it. Thank you for listening.